We're going to go back and talk about residuals. So residuals revisited. The linear model assumes that the relationship between two variables is a perfect straight line. This is because the linear model is a linear equation, so if graphed on its own, will give you a perfectly straight line. The residuals, or the differences between our predicted y value and our actual y value, are the part of the data that hasn't been modeled. Those vertical differences show us what our model didn't catch. So what are the other underlying variables that exist that will have an effect on the relationship between our two variables. So our data is represented by both our model and our residuals, because the model is showing the relationship between the two variables that we are interested in, and then the residuals show if there are other variables that play into the relationship. If we rearrange this, we end up that our residuals are equal to the data minus the model, or using symbols, where E represents our residuals, we have y minus y hat, or our data value minus our predicted value. Residuals help us see whether our model makes sense or not. So, is it linear? Does it make sense? Are these two variables related? Should there be a relationship here? The residuals help us determine whether or not that is true. When a regression model is appropriate, nothing interesting should be left behind, so it should end up being completely random. After we fit a regression model, we usually plot the residuals in hope to find nothing. What that means is that our x-axis will stay the same. So our x-axis will be our x variable. Our y-axis will now be our residuals. So the y minus y hat will be on our y-axis. What this will show us, it'll show us if there is a pattern which will represent other variables that our model did not catch or that have an effect on the relationship between our variables. We're hoping that if our residual plot has no pattern to it, then that means that we have appropriately found and represented the relationship between the two variables. So looking at the residual plot from our Burger King example, we have the protein on our x-axis because that was our x variable, and we have our residuals on our y-axis, and yes, it goes both positive and negative. In this case though, we see a completely random residual plot. There's no pattern here, there's nothing we can say about the residuals or any way that we can describe it other than saying that it's random. This is what we're looking for. We are hoping to get a random residual plot because this tells us that our data is actually linear and the linear model is truly appropriate in representing that relationship. If there were a curve here, that would indicate our linear model is not appropriate because our data are not actually linear. And if that's the case, we would have to re-express the data somehow, which again we'll talk about in Chapter 10. When using the linear model, we have to plot our residuals, and we have to look to see if they are random or if there is a pattern, because this will tell us if we can actually move ahead and continue using our linear model, or if we need to take a step back and try and re-express our data. So as long as it's random, we're good, we can move on. If there is a curve or a pattern, we cannot use our linear model and it will not be appropriate. So looking at the variation of the residuals. The variation of the residuals tells us how well the model fits. So if our residual plot is random, that's good. But there are, of course, different levels of strength. So we might have a really strong relationship and we might have a weaker relationship. And the variation in the residuals kind of gives us that idea. So all regression models have a correlation between 1 and -1, which does measure our strength. Can we use the correlation to gauge where our model falls? Is the model fitting well or is it not fitting well? And yes, we can. If we square the correlation, the sign goes away and we're left with a number between 0 and 1. This number is called r squared because we squared r, our correlation. So what R-squared does is it gives us a fraction of the data's variance accounted for by the model, and it's often given as a percentage. What this means is that R-squared shows how much of the variance in our y variable is accounted for by the model, or in other words, accounted for by our x variable. So looking at an example of this, using our Burger King example, we had a correlation of 0.83. If we square this, we get 0.69 or 69%. This means that 69% of the variability in the fat content of Burger King sandwiches is accounted for by the variation in the protein content. In other words, 69% of the variability in your y variable is accounted for by the variation in your x variable. This is how it will always work. So when you are explaining or interpreting your R-squared value, you must always say that R-squared represents the variability of y accounted for by the variation of x, or the variation in x accounts for this percentage of the variability in y. Either way, you can say it going forward or backwards, but that's what you have to say. I will be very picky when grading how you interpret this. There's not much variation from how you can say this. So let's try another example. Going back to the house example. So our house equation was predicted price. That price should have a hat on it, I'm sorry. But the predicted price is equal to 0.9564 plus 122.74 times the size. We end up getting an R-squared value of 71.4%. So what does this mean about the relationship of price and size? Well, again, our x variable accounts for the variability of y, or the variability of y is accounted for by the variation in x. You can say it either way. So here I have it written as the variation in the size of the house accounts for 71.4% of the variation in the price of the house. So again, the variation in x accounts for the certain percentage of the variation in y. What happens if we change our units? If we change our units of the size of the house from square feet to square meters, does the R-squared value change? So R-squared is based off of our correlation, and correlation has no units, so changing the units will not actually affect R-squared. However, our slope does have units, our y over our x, so in this case, dollars per size. So changing the units will absolutely change the slope. So again, R-squared does not change because correlation will not change, but the slope will change. Using our regression line. In our house example, we had, again, this equation. Can we find the size of the house using the price? So can we solve for x? No, we cannot. The slope is determined by the vertical errors or the differences in y. So to make a reverse prediction, we would have to find a new line focusing on the differences in x. So it only works one way. You can only use x to predict y. It does not go backwards. Finally, reality check. Is regression reasonable? Statistics do not come out of nowhere. They are based on data. They are not made up. You can't just decide something. You have to use the data that you have and follow what the data are telling you. The results of a statistical analysis should reinforce common sense, not fly in its face. Think about the price of a car and how old it is. It makes sense that as a car gets older, the price goes down. So if you have data that's trying to tell you something different, you have either learned something new or your analysis is wrong. So you want to make sure that it makes sense. Think about it. Use your common sense. Use your prior knowledge. When you perform a regression, think about the coefficients and ask yourself whether they make sense. So is your slope positive? Should it be positive? Is it negative? Should it be negative? Is it too big? Is it too small? Pay attention to it and ask yourself, does it make sense? That is it for Chapter 8. So I will see you guys tomorrow. Have a good night.